Okay, thanks so much, and yeah, thanks for me as well to the organizers for inviting me, and it's been a great conference so far, and I enjoy meeting a lot of people that I worked with on the quantum benchmarking program and seeing a lot of that work again and talking with them and so forth, and a bunch of new people as well. First time at IPAM, so it's been great. And so I'm going to tell you about some of the work that we sort of started with the quantum benchmarking program and have been continue to work on. And my thesis is that having real applications and compiling them down to logical circuits and doing analysis on those real logical circuits is a very important thing. It's going to tell us a lot about what we can do, the value of quantum computation, but it's also going to tell us a lot about the architectures and the trade-offs we see in the different architectures. And so that's kind of what we're trying to do, trying to build a set of tools. And it's a lot of work because there's a lot of pieces to it, and we're partially through that process now, and so I'm going to give you a highlight into where we're at this point. So when I was thinking a little bit about like how do I bridge the gap or talk about bridging the gap between NISQ and fault tolerance, we have a little bit of work in the NISQ era, which I'll tell you about, but most of the work is sort of focused around fault-tolerant architectures. And so one of the things I thought of was that there are a lot of differences between NISQ and fault-tolerant, but the themes are somewhat similar in some sense. So like in NISQ technologies, you've got systems. They're the fancy looking like this, but they're large systems, and they focus on some number of qubits. And now you start to talk about in the fault-tolerant area, you talk about large systems, large fault-tolerant systems with many components and so forth. And this is essentially a cartoon, but this is what maybe a fault-tolerant quantum computer layout would look like. For example, this is from the Google work from Craig Gidney. You got qubits over here on the NISQ side, but on this side you have surface codes or logical qubits and so forth. You have classical processing we have to do, like VQE. We've heard a lot about that this week. You also have to do classical processing for syndromes, and for example, this is a picture from some of the Riverlane work. And then you have architectures. Here's the Quantinuum architecture. It's a small architecture, something you built. And this is a concept of BlueJ, one of the large IBM machines. I think this is just an artist rendering at this point, but you can talk to IBM about all the details of what that looks like. So, what's common between those things? Well, there's a lot of different things, but a lot of the tools, a lot of the design that we have to do, there's a lot of common themes. So we have to build circuits, we have to compile those circuits, we have to design algorithms, we have to design architectures, we have to do resource estimation. There's a lot of hardware, software co-design, there's control systems, there's classical processing and all. And so the question is can we learn some of the stuff that can we take some of the stuff we learned in NISQ era and apply it to the fault-tolerant era? It's going to be different, but there are going to be a lot of some of those things. Okay, so that is motivation. What I want to talk about today is I want to tell you a little bit about some of the architectural analysis we did for near-term architectures, an internal project we worked on for a bit. And then I'm going to talk for the bulk of the time about sort of the circuit generation and analysis work we've done starting in QB. This tool called pyLIQTR that we developed is sort of the framework of a lot of that. And I'll tell you about what kind of circuits we can generate, but then also talk about using that to analyze different fault-tolerant architectures. Okay, so a couple slides on the near-term stuff. So the first thing is that the focus here really is on these same sort of architectures, the things that are 50 to 100 physical qubits. We're really focused more on the architecture and less on the qubits themselves per se. That's somebody else's job. But the idea is we want to take details about these architectures and feed them into details about the qubits and then what they can do and feed them into these architectures, for example. So these are early architectures. We want to think about how you might optimize them, how you might look at the different trade-offs that people have when they build these architectures and how those different trade-offs impact resources and things like this. And here again, we're going to do this by benchmarking particular instances of circuits. This case, for these architectures, we're talking about variational algorithms like QA-OA and things like this. And so, we looked at ion trapping architectures, and we also look at superconducting qubit architectures. So here's the ion trapping architectures, different versions of ion traps that we looked at. So you could think about something that's like a fully connected architecture where all qubits are all-to-all communication. there's this idea of a reconfigurable architecture where you can put everything into a line and communicate across all the ions, or then you can split those into multiple things. And the idea here is that a fully connected architecture allows you to sort of communicate across any of the qubits here, but that limits your parallelism and may slow down your gates. These smaller guys will allow you to do more parallel gates, but also maybe faster gates as well. Then you have these zoned architectures. Then you have these QCCD architectures where there's a small number of qubits in each trap, and then they get shuttled around the architecture to do qubit gates. And so there's different trade-offs here, and we wanted to evaluate sort of what these architectures meant and how in terms of time to solution and other things and so forth. So there's a number of things, but I'm going to only show you one graph for this. This is a 48-qubit QAOA problem. We looked at a base architecture where there was no constraints, but then each of these adds some sort of constraint. So for example, in this architecture here, you have to split the ions, you have to move them, shuttle them through the architecture. These constraints here, you have limited parallelism in certain cases if you have to do certain gates, for example. You also have to do cooling, for example, before every gate, we would have a cooling pulse, for example. And so you can look at what the critical gates are in this kind of architecture, right? So for when you have no other constraints, cooling is a constraint, is the biggest constraint. When you have a single chain, then cooling and 2-qubit gates are the biggest, most critical operations. But then some of these architectures here, where you have grids and ladders, moving becomes the most critical time. So all this really means is like 20% of your time, or most of your time, you're doing these types of gates. So it really depends on your architecture. And the other thing we did, and I don't have a graph for this, is like, you have some base set of assumptions for each of these things. If those assumptions are off by a factor of 10, either plus or minus, that's going to really tell you something different about what these architectures are. So the idea wasn't so much, which of these architectures is the best, but as you start to evaluate your trade-offs, you can see how critical these different operations are. Yeah, Brett.
In brief, for like moving, are you solving a hard scheduling problem to know exactly how these things should be moved, or you're kind of saying move cost is approximately square root of n or some other form?
So the way this is done is there was like I'll talk a little bit later about what the scheduler is, and it's sort of the same sort of thing in this case. So we are actually contemplating the operation of moving. So you execute a program, you get to the program, you realize, okay, here's this guy and this guy, they happen to be in 2 different wells. So I have to add split operations, and I have to add move operations. Those moves take a certain amount of time. Those moves will block the lane, for example, so nobody else can do that. So we are solving a scheduling problem. I'm not sure it's hard because it's generally use greedy methods, first come, first serve, and things like this and so forth. So it's not an optimized over the whole circuit sort of thing. It's sort of using heuristics of some sort to say, we're going to go vertical and then horizontal or something like this, and simple things like that. But it does account, but that's a good point, it does account for the fact that there is dynamicism in the operations that are involved with doing moving and everything else. Yeah, thanks. Okay.
Just so I understand the spot a little bit better, is this, I imagine that some of these operations are done in parallel. So
depends on the architecture, yeah.
So then the vertical axis is this, what is it?
It's not, now that I remember, it's in seconds, so it's not sort of, it shouldn't add up to 1. I guess maybe that's your question. I had that question too when I looked at this again. So it's the amount of time, essentially what we did was we zeroed out all times except for each of these individual times, and we said, okay, how much different does the runtime go if you start to do things like this and so forth. So it's really the critical path of any of an execution trace for any of these algorithms, right? And so the critical path here is just moving the operations, and you can see the relative difference between moving and say doing a 2-qubit gate, which is like 20 times larger. Does that make sense?
Okay. Yeah, I think critical path, maybe that.
Yeah, it's more the critical path, but it's done by like sort of saying, okay, well, what if everything else was gone? Yeah, and even the parallel operations would be gone too. So yeah. Yeah.
So how much is everything else, so that we know what kind of percentage this is of the whole?
Well, this is everything, right? But you shouldn't add up each of the numbers to get 1. This would be the total runtime you get a gate time on each one of these things, right? So you say a CNOT gate takes some number of milliseconds or microseconds in this case for an ion trap, and you can look at the whole circuit, and the total time is that. So the total time on this architecture is just the sum of all these guys here.
Oh, I see.
Yeah.
That really is everything, and you sum them together, and that's your
right.
runtime.
This is everything, and then we're just but don't think this is not a percentage of the time.
No.
This is the total
The actual runtime.
seconds. When you add everything up. Yeah.
Great. Yeah, sorry. Thank you.
Well, sorry, it's not normalized to everything, right? That's the point. Yeah.
There's some operations that just don't have bars. Those aren't available on those architectures or something?
Well, no, they don't. They're not needed, right? So this is like a baseline architecture. It doesn't have moves in it. You just don't have it, right? So there's zero.
That's what I mean.
Yeah, zero. It's not that it's not available. It's just that it's zero in that case. And some of the architectures don't need moves, right? So they're zeros as well, right? So like these architectures don't need moves. These ones need splits and joins and things like this, since you have that. And then we're assuming cooling has to happen for everything, every cooling pulse. And we did this. I think I guess one of the architectures we looked at, they did cooling on every single pulse in the physical experiments. I don't think you would need that now. Most people don't. I think you don't need a cooling pulse for every single 2-qubit gate. So anyway, cool. Thanks. Okay, so we also did something for superconducting qubits. And here are different topologies, right? And so it's different in superconducting qubit, right? I mean, the gates are faster, but the connectivity is limited, right? And so here are 4 different ones. We did a few other things too. But the problem with superconducting qubits is that if you want to interact 2 qubits, they're not currently directly attached or directly connected. You have to do swaps. So you swap gates, and swap gates take a number of CNOT gates, for example. So 3 CNOT gates for a swap. So that adds to the number of 2-qubit gates. And so you can track that as a function of the size of the circuit. And here we're doing something similar type of architecture, but here we're doing different size circuits. So everything from a 10-qubit circuit up to a 10-qubit circuit up to a 70-qubit circuit. And then the different lines here are just different architectures. And there are a few more here that aren't listed here. Baseline is just like, well, we can just interact any 2 qubits. So there is no swaps. And so that just grows linearly with the size of the circuit. But then if you start to put things on a line, for example, it goes like more quadratically. And so you've got about 8,000 times, factor 8 more 2-qubit gates for this circuit versus for this circuit, right? So, and of course, it kind of goes as you would expect, right? The architectures that are a little more connected, like the grid architectures versus this older IBM architecture, work a little better and so forth. So this is kind of what we expect. It sort of gives us some amount of, you get a good handle about how this goes, but yeah, more connected architectures are better. Yeah.
Wait,
Yes.
did I miss something, or is Ithaca not on the graph?
That's heavy hat.
It's not.
Heavy hex.
Heavy hex, yeah,
There we
that's
go.
right, heavy hex.
Thank you.
Sorry, thanks. Yeah, I haven't seen that in a while. Yeah, Ithaca is heavy hex. This is an example of a particular ship. The heavy hex architecture is just a repeated tiling of this. We did Sycamore, and I think we did also a grid, which is very, very, very similar. I think it's just the boundaries are a little bit different so far. Yeah. Yes.
Sorry.
The justification for the bus NNN architecture, is that like a resonator?
This is something we dreamed up. So the idea here is that you would have some network. These guys here would have some sort of crossbar where they can communicate anywhere. And then if you wanted to communicate, say, between a qubit here and a qubit there, you would sort of move things through this. This is a 2D version of it. The 1D version, I think, is kind of the inspiration, was the fact that one thing you could do is you could think of everything on a line or everything in a grid, and you could do things like, you could do a permutation that allows you to sort of like, through the course of all the steps in the permutation, it has every qubit next to every other qubit, right? So some number of steps will give you sort of an all-to-all thing through something like this. And so that can be done on a grid, that can be done on a line, but it's more efficient to do on this and so forth. So this is not an actual architecture. This is something that Ben, who worked on this, dreamt up and ran, and it seems to do fairly well. It's one of the better ones in this case, but here again, it's application. Yeah.
Yeah, so I assume this is unitary compilation of the circuit into the connectivity that you have. But there is a more efficient way of just like preparing a JG state, for example, in constant depth and then teleporting a CNOT across.
Yeah.
would that save you a lot when you compile on like those connectivities, you think?
Yeah, I mean, I think it would. Yeah, I mean, I think the idea then is you're sort of you're preparing something in to begin with, right, in sort of the background, right, and then you're doing these 2 qubit gates. But it depends on how what the connections look like, right? So, for example, if you've got like a lot of different random connections across the grid, then that probably doesn't help too much, right? Because then, but if you have sort of like a, really unconnected things that you want to go communicate between here and here, then bridging, that gap with some sort of distilled pair or something like this might be a good idea. But yeah, that's right. So I mean, I think here again, there are a lot of different architectures, a lot of different things we could look at, and the motivation here is to look at some of them, and as we start to new things emerge, I think the methodology allows us to do lots of those things. Yeah, Peter.
Yeah, so I'm hoping you could comment a bit more on the motivation here. So I'm picturing that like when IBM is designing Ithaca, they might have a like close co-design with syndrome extraction circuits in mind, right? Like those two.
Yeah.
So maybe they're not really, or or Google Sycamore, right? It's laid out for the particular
surface
syndrome
code.
extraction circuits.
Yeah.
So given that co-design is probably very tightly coupled, how do you think about or the motivation for this this kind of like?
Well, I think you have to
assessing
ask the hardware
architectures?
designers. If I understand correctly, and then somebody from IBM can tell me if wrong, I mean, I think the idea here was that there was problems with frequency crowding, right? And so this allowed you to sort of have, to solve that problem somewhat, right? So it wasn't necessarily motivated by a better connectivity. It was more because of this issue that, there's a lot of shared frequencies, and these didn't have like tunable couplers at the beginning and things like this and so forth. You're smiling, so it's all solved now. So this is an old architecture, that's fine. So don't take too much into it. And this work was from like 3 years ago, anyway. So.
But I'm not an expert on that side of things, but I do believe that roughly that's what happened. Like they built this, but it was easier for them to build lower connectivity at the time, and that now higher connectivity is much easier with the approaches that they're taking.
I guess in going the other direction though, of like it seems you're attempting to assess these architectures according to circuits.
That's right.
So given that they will probably have very specific circuits in mind that are, designed for these layouts. How do you think about how you might?
Well,
assess?
I think this was meant to be like NISQ circuits, right? So the connectivities are more random based on what the circuits are. But I think the point that I'm taking from you, and this is certainly something we thought about a lot, was that probably for fault tolerance, you're going to design your circuits for error correction, and that's exactly what IBM's doing now, right? They're designing their new hardware to do, the gross code and things like this that have weight 6 connectivity and things like this, and so that's probably more. Yeah, they're designing it around the error correction gadgets and things like this. Yeah. Thanks. Cool. Okay, so now that's great. Good discussion on this part. Now we're going to get to the more fun stuff, I think. So the fault tolerant stuff. So we saw some of these pictures already. I think most of them, except maybe the top one. And the idea is what I want to make the point, and Nicole was making this point on Mondays, is that what's really important is that we want to start from an application that we can say something about, so we can say something about this value and things like this and so forth. And so this is one of the applications that came out of the quantum benchmarking program, and this sort of cyclic ozone problem. So it has different instantiations of different sizes, and then there's this wonderful quantum benchmarking graph, thanks to Matt, for how we break this thing into different subroutines that we might execute. Some of these subroutines, or most of them, are going to be classical, right? Here's the instance. So one particular value of this. It's broken out into all these different things. Some of these can be alternatives. Some of them are all used, but part of them will be quantum computing. So the idea then is to take these things out and figure out how they fit into this overall workflow, and then maybe go into this in some detail to say, okay, well, what's this going to cost to do, right? And so from the problem, we can get the parameters that go into this. We can understand what's needed by the quantum circuit, what's the fidelity needed, how many bits do we need, and all these sorts of things associated with it. So I think I put this in the last minute. I think people, I don't know how many, most people probably know what block encodings are, but maybe I'll spend a second to say what they are, because most of our constructions are based on block encodings. We've heard a lot about triodorization. We also have some support for that, but most of the things I'll talk about today, or maybe all of the things I'll talk about, are in these qubitized type environments. And so the basic idea here is that if you have something that you want to implement, maybe it's a Hamiltonian of some sort, you can't directly implement that as a quantum circuit, so you have to do something. You have to either, in triodorization, you exponentiate the Hamiltonian, but here, the idea behind qubitization is that you embed that into a larger system. So you add some ancilla degrees of freedom, embed that sort of in the upper left-hand corner here, and then these ancillas, the idea is that you project into that subspace. And if you project successfully into that subspace, you apply the operator. If not, then you applied some sort of junk, and that's sort of the zero part is the projection here, and the one part is the projection into the junk state. And the idea is to make the probability of projecting into the wrong state very, very small. And that depends on a lot of things like details of what this operator is and so forth. So another nice thing you could do with this is this notion of quantum signal processing, or QSVT. And the idea is that you can apply a function to like the eigenvalues of this operator, and by doing that, you can do something to it. So for example, you can do quantum simulation. We heard Itai talk about that yesterday. And really, you find some polynomial, and you apply these phase rotations in between different applications of the operator, and that applies this function like phase estimation, like simulation, or you can do things like pseudo inverses and many different things. And so then the question really is how do you do that? And it's really a function of the order of this polynomial, how many times you split it up into pieces. And that's what this is sort of showing here. You're repeating this again with these small phase iterates here that come from the polynomial expansion of this function that you're trying to apply. So that's called QSP or QSVT, depending on exactly what you're trying to do. And at the end of the day, I think we saw this picture already, is then that's just a repeated application of these block encodings plus something else. This is not this is a phase estimation circuit, so it's not using QSVT, but it still requires repeated applications of these operators. And in this case, you're breaking this block encoding into this LCU type construction where you're pairing some coefficients of a Hamiltonian, for example, and then doing a select, apply the operators from the LCU, and this is repeated over and over again. And one of the things that comes out of this is that for resource estimation and for evaluation is the fact that there's two key things that we care about here. And the first thing is like, well, how complex is this whole thing here? This LCU can be fairly complex, and I'll talk more about that in a minute. But then the other question is how many times do I need to apply this? So it really comes down to those two things, and they're related, right? The number of times I need to apply this is a function of how complicated the thing you're trying to apply is. But also how complicated this is, of course, is a function of how big your system is and so forth. So those are typically the two things we try to estimate. We try to estimate details of the circuit of this thing here, and then do some analysis to figure out the number of times we need to do this. Okay. And so in terms of like doing that encoding, there's a bunch of different methods. Some of these methods came about because of optimizations to older methods. Some of them came about because they fit particular problems better or worse, and so forth. So if the application instance that I talked about, here's sort of where it comes in, and then you have several choices, right? Doing a poly LCU is very simple. That can be applied to almost everything, but as I'll show in a second, it's very inefficient. So it doesn't, in terms of the runtime you would need and how big the system is, it's, well, the system maybe not that large, but it takes a lot of runtime. So that can be applied to certain things. We have a paper from my colleague, Justin Iluninsky, looking at NMR dynamics, and he uses that method for that. There's also second quantized methods, first quantized methods. Those are all going to be applied to different things. Then you have the different bases that you can apply. And then we also have some people that were working on differential equations and things like this. And those sort of fit in here. They're quite different problems, but they also fit into this notion of, oh, I have to break things into a block encoding of some sort and use that block encoding. And so here are some of the problems from quantum benchmarking and how they fit into these different things. And so one of the things we really wanted is the ability to sort of try out all these different things, so to have implementations of these things. And so some of them could be used, like we looked at second quantized sort of these dual plane wave basis linear T paper from Google. That was one thing here, but we also looked at compared that against first quantized, and I'll show you some results of that. Okay, so that culminated into the software that we were building called pyLIQTR. This came out of a lot of conversations we had in quantum benchmarking. I know we had many conversations about like, oh, we really need a software to help drive resource estimates and so forth. And so that's really came out of that effort to do this. And so this is meant to be a software that gives us the circuits for all these sorts of different problems that we're talking about. And so it includes a lot of things like how do we generate the Hamiltonians? How do you take a particular, how do you specify a particular type of Hamiltonian, then how you actually generate that Hamiltonian using tools. And of course, some of these tools are tools that are already in the literature that we're just making use of. Then how do we do the block encoding, right? There's a lot of different ways, just the ones I just showed you. And then apply algorithms to them, so like QSP, QSVT, for example. And then there's a lot of other stuff that has to be done. Classical prep, for example. These angles that I talked about for QSVT, those have to be generated. You have to do this sometimes, this Clifford plus T synthesis for arbitrary rotations. We have code to do that. And then this is the electronic structure package that helps build some of these dual plane wave Hamiltonians and so forth. So all these tools are sort of in here as part of the package. It is open source, so you can pip install it here. We also have a repo of it as well. And a lot of this is based on Qualtran, and it was Circ first, then Circ FT, and then Qualtran as sort of our way of representing circuits in the background and so forth. And I think we were some of the first users of Qualtran because Ryan and Tanush came to one of our meetings once, and we got really excited about using it, so we started using it right away. Okay, so one of the first things I do, if you want to look at pyLIQTR, what I tell people to do is look at the notebooks, the Jupyter notebooks. And so there you've got different notebooks for a lot of these different problems that I already talked about. And what's in these notebooks is it has some nice pictures that tell you what the problem is trying to solve, how you might set up your own problem or how those problems are set up, how you would generate circuits, the block encodings for them, how you would generate circuits for it, how you would do some analysis for those circuits and so forth. And so there's notebooks for each one of these things and some other things as well. Okay, any questions so far? Any other questions before please jump in again. Okay, so one of the things, so there's a lot of analysis that we did, and I'll show you just some examples of that. So this is a block encoding for this magnesium corrosion problem that we defined. It was defined by QB. A lot of the collaborators here are here in the room. And so we compared against this linear T block encoding. This is from the Google paper from, I think, 2019, to a generic poly-LCU. And you can see here there's a huge savings to using this linear T construction. This is just in the T count. If you look at the circuits for the T count as a function of the number of spin orbitals. And there really isn't much of a penalty in terms of the number of qubits, right? So we're only able to look at a small system size for the generic LCU, but you still can see that the way the linear T scales is still sort of basically a function of the spin orbitals and just a few more things, yeah.
So what type of Hamiltonian are you thinking about for this problem?
It's this I guess this dual plane wave Hamiltonian that describes it's based on let's say it, I guess yeah, I think it's second quantized in the dual plane wave basis. Yeah, that's what it. Yeah, it's this one here. It's periodic basis linear T dual plane wave basis. Yeah. Okay, so Here's some more details. I think these are talked about in the paper. This is this paper that we wrote with Boeing and HRL and other folks. Okay, so we also extended this now to the first quantized basis, and so here the idea is that the t counts in logical qubits should be logarithmic in the number of plane waves, although they're linear in the number of electrons. And so here there are 4 problems, and I'll refer you to this paper here. Nam was here. I think he's not here this morning, but he can tell you more about the details of this. 4 different instances of these problems that we defined, that it was defined, and we see a good savings in terms of the t counts by, depends on the problem. It's either 2 orders of magnitude or order of magnitude difference. Logical qubits better by not quite an order of magnitude in most cases. And also what's important is the Hamiltonian norm goes down as well. That dictates how many times you need to repeat something to do phase estimation or dynamics and so forth. So that's probably didn't, I think we were expecting a better savings here, but it was still considerable savings.
So is linear t like a heuristic that you have theory about that says that this should be better or?
Theory, I don't. Maybe we do. Wouldn't be able to communicate it to you. But linear t comes about because a lot of the ideas, a lot of like the QROM ideas, and came about in that paper, and the scaling was a linear function. I mean, the number of t gates was a linear function of that because of the way they use the QROMs and so forth. The linear function of the number of terms in the Hamiltonian, for example, and so forth. So, yeah, there is some theory. I don't know if you know this paper from Babush et al. In 2019. That is the basis of all of this. Yeah.
So just to confirm that, so you're using the unary iteration circuits and not the select swap QROM implementation.
Yes, it's the circuit that's defined in that linear T paper, which uses that's right. They use these fermion this Mariana type operators. Yeah.
You can sometimes improve upon the T complexity with later developments in the QROM.
Yeah. I mean, there's lots of trade-offs, right? You can parallelize things a lot more and so forth. But yeah, that's right. Yeah. Okay, so now I want to go into talking about the analyzing fault-tolerant architectures. With this, the notion is that what is your first thing I want to ask is like, what's your architectural model, right? So we talked already about gate counting. That's great if you want to look at the complexity of your circuit and see how your algorithms are doing and so forth. What's also great is it's very easy to do. You can, most circuits will always, what you want to do is decompose them into Clifford plus T. And a lot of times only T gates are reported in this case. And you don't necessarily have to build a circuit to do this. A lot of times, most people that report T counts are actually looking at the pieces and just counting each of the pieces and then multiplying it together and things like this. So you don't have to build a circuit, although I think it's good to have a circuit because then you can really double check all the details, make sure everything's all there and so forth. But that's very easy. pyLIQTR supports that. If you have a circuit, you just call estimate resources on it and it'll spit this out. It will use some of the tools that Fault-Tolerant gives you to sort of do analytical estimates so it can be very fast. The next thing you might do is you might look at something that's sort of inspired by game of surface codes. The idea here is that you do you have a bunch of you have some ancillary regions, and then you can communicate and you can do a measurement across all the qubits all at once. And the idea here is you push all the Cliffords to the end, so you're only ever doing T gates, but you're doing you're only able to do sequential T gates and so forth. So I say that the Microsoft Azure resource estimation tool is an example of this. I don't know if Michael you would agree, but what I always assumed when I looked at that tool was that it's assuming sequential execution of T gates and then there were no Clifford gates in the estimates. And so this is to me what I think of when I think of game of surface codes. I mean, it's not. I mean, I don't know if this is what you had in mind, but this is.
I guess what we do there is we call it parallel synthesis. Yeah. And it's not that different, but basically each time there's a fine angle rotation, that is compiled off the main block.
Okay.
So you can do lots of keys at the same time. by using this trick, but it's not very different in architecture.
Okay, okay. This wasn't supposed to be an exact thing. It was just for notional.
We can talk about it after. I think it's not the best thing that you can possibly do in our book, right?
Okay, got it. What I'll talk about now is really sort of more, I think, inspired by this, the idea that you have gates, they can take different amounts of time, they exist in different places, and so forth. So this is the scheduler. And then also we supported this resource graph state compilation we heard a little bit about on Monday from Katarina, and we could take our circuits and do that. So so the idea is you have a notebook, you generate a circuit, you can just count the gates, and once you count the gates, you can do a tool that just takes that as an input, for example. And we did some of this. We didn't do a lot, but we did some of this. Mostly, our job was to feed these guys here, so we spent more time doing this. And so the bench queue and sort of was supporting the Rigetti team, was also supporting some other teams as well, but this is a good example of that. And so you can do a number of different things. The scheduler sort of fits into here. You have to have a circuit in order to use a scheduler, but you also have to have a circuit to do this as well. So I'm going to speed up a little bit. What's the idea of scheduling? The idea of scheduling is you have a circuit, say, in these gates. Some of these gates commute and some of them don't, right? So these two gates here at the beginning, they can commute, so you can execute them in either order. It's fine, based on which ones are ready. These two gates commute, these gates commute, but these two, the second and third one, do not commute, right? So you build a time and dependency graph for this, and then basically a scheduler is just taking things off this graph. You can assign times for each of these gates, for example. There's not just, it's kind of like the idea of moments in circuits, kind of like this, but here we can define a different time for every different gate, right? And so, and then we can also put in physical constraints. So for example, we can put in constraints about factories, we can put in constraints about channels that are being used and things like this. And so the idea is to put in a number of different constraints that describe a number of different architectures. We can then get out things like the execution time, depths, number of qubits used. We can also really look at the profiles of how things are executed in parallel and things like this. Yes?
How are you handling things like, for example, if you're using cultivation, you might want to repeat until success, things like this, and that causes you have this wait. Okay, cool.
We don't do cultivation yet, but what you're asking about is what's the probability of success, right? So the idea there is that you have a factory, you have a piece of code that describes that you can then specify how that factory works. So so some of the things you can do is you can say, well, it takes a certain amount of time to make one state. It takes a certain amount of time to apply that state, which is pretty typical. And then then it takes a certain amount of qubits too. We want to track that as well. But then there's also a probability of success, right? And so this thing is a little engine running in parallel. And so you can have some number of them. You can have one of them. You can have 5 of them. You can have 20 of them. Whatever. There's also buffers too, right? Because the way to get around this non-unity success probability is to buffer states and then use them as you take them. And so you can also say, well, I want to have 5 deep buffer, for example, or maybe only I want to have 1 or something like this and so forth. So that's how we would do that. Yeah.
And your scheduler can handle the fact that it might need to wait and install a bunch of
That's
gates
right.
to get it.
So here again, hardware constrained is anything in the hardware that sort of stalls the timing, and this, it goes every time you need to do a gate that needs a resource state, it has to go to one of these factories. And here one of the ideas here is that for each of the different blocks that you may, and I'll describe this in a little more detail, but the idea here is you take a bunch of qubits and put them into a block, right? So in a LDPC code, this is sort of a block of an LBC code, but you could also think about just blocking together a number of superconducting qubits, for example. And the reason we might do that is we're curious about locality, and I'll show you some results that says something like that. But so you map a certain number of qubits from the circuit to these blocks, and then you attach factories to these blocks and so forth. So if this factory right here, this one only has 1 factory, so it has to wait for that 1 factory to do it. You can also apply all factories to all qubits, for example, or blocks, and then you have this shared sort of architecture and so forth. Yeah. For right now, we're just using the table from Latinsky's paper, but we can also use cultivation. I'd like to understand cultivation a little better. I noticed in one of the later papers maybe there's some code for it, so maybe we can understand a little better. I don't know if I understand the timing of it yet so much. I think the way they describes the resources isn't so isn't as obvious to me, so maybe some more conversations with you guys would help me figure that out. But really, it's just a matter of putting these in the table. The idea here basically is that you look at the circuit, you figure out what you need, right? So you go in this table and you say, well, I have a 10 to the minus 4 error rate. I need a logical error rate of something, so let me pick one of the guys from this table. So you do that for every application you run and so forth. Same thing with the codes. You know, if you have a surface code, it's really easy. You just pick the distance, and those can be different sizes. But there's no reason why you can't define something more complicated. I'm going to show you some results for the BB codes, and in there we have the gross code and 2 gross code, and you can pick the different ones. Yes.
So 2 questions. One, is there any scintillation here for the production of like Toffoli states?
No. I mean, right now it's factories. Well, actually, the idea of the factory is pretty generic, right? So if the factory generates a Toffoli state, and that's what it does, then if you can describe it in terms of these parameters, then you can do that. So it's up to you to come to me and say, well, it's going to take this amount of time, and you can describe it this way. You can also think about it. Maybe your architecture needs cat states, or maybe they need an EPR pairs to do something. You know, these factories are all, I mean, generic in that sense. So you can always build that up and just say, this is the resources it needs, this is how long it takes, this is how I can buffer those resources. And then you can just attach each one of these to a different gate. So you just say, well, you know, maybe I need to do a measurement, I need a cat state, well, I just attach that factory to it. So it's going to be generic in that sense.
Yeah, that's a nice lead into my next question, which is, we might also think about factories that can produce reaction-limited states, right, automatic states. Has the team thought about that at all, or like how we might think about compiling with your factories?
Well, you mean there's going to be a latency, right? Each of these factories produces a state at a time, right? And so there's a time it takes, a production time to do that, right? So is that what you mean, right?
Sorry, by automatic magic states, I mean magic states that have auxiliary ancilla qubits that are used to control later functions. So there's more exotic classical control structures that are needed. You might need to also have storage space to store those qubits.
Yeah. If you want to build up something, you have some substates that takes a lot of. Yeah, I think that can be represented by a factory of some sort. Yeah.
And then related to that, so then is there a classical control, like a time penalty also within the simulation framework?
Decoder time, you mean?
Decoder time or something? No, not right now. That's something we could do, right? I mean, I think that the decoder time would then be a sort of a feed forward timing on a future gate, right, and so forth. But that's pretty easy to do. We don't support that now, but that's something you could support. That's a good idea. Yeah.
Great, thank you.
I'll show you how to do that in my talk.
Okay, sounds good. I want to incorporate that. Okay. How am I doing? 3 more minutes? Okay. I do want to get to some of the results. I only a couple charts, so this is good. So we looked at a few different architectures. Here again, this is not meant to be a comprehensive study, not as comprehensive as what Katerina did. It's really here to show you some of the capabilities, and we're hoping to do more and more of this. We're making improvements, adding new features, also making it faster, which is going to be important for certain things. But 4 different things, so like a linear architectures, grid architectures, and then the 2 different differences here is like whether the factories are attached directly to the blocks or whether they're sort of shared across the whole architecture and so forth. And then looking at 2 different instantiations of things, so superconducting qubits, sort of a standard surface code type of architecture, and here's sort of what you'd expect from that. Within blocks, you can do arbitrary operations between any qubit in the block. We keep these small. Bicycle architecture, taking all these parameters from the paper. Some of them were derived based on all the times, and you can only allow 1 operation at any time within a block, and 1 between blocks and so forth. And then for these, we assume that the Clifford's been pushed to the end, so there's 0 Clifford time. So here I just have a couple charts showing results. We looked at the Heisenberg problem, not because it was the best problem, because it was the easiest one for us to scale. We can, in principle, do any of the things we get out of pyLIQTR. Some of them take longer to schedule than others, and so that's one of the challenges we have. But you can start to look at things like runtime, right? So as a function of the size here, I think I used 10 qubits for superconducting qubit and 11 qubits for the bicycle code. That was the natural size. And the timing, these circuits are very serial, so you only actually need like 2 factories in order to get these to work well, and so that's what you kind of see even here. So the blue here is like private factories. So there's lots of factories. If you have, this guy here has, I don't know, maybe 64 modules or something like this. So he's got lots of factories, and that's why if you look over here at the qubit count, it goes way up because he has more factories than he needs. 1 factory is a little bit slower, and then 2 factories and 4 factories, there's no difference, right, in these things. The BB architecture is slow because of you have to compile basic operations down into these bicycle operations, so there's many operations that are required to do that. But of course, it's very, very small, right, compared to really dwarf in terms of the size. And so I don't think that space-time trade-off is better than Unity yet, but I think certainly building smaller systems is good.
Kevin, can you talk about the qubit mapping strategy for these?
Yes. I promised you this already, so I will talk about it next. Okay. Yes.
Sorry, just back one real quick. Is the time axis correct? It's billions of seconds?
So, yes, I was hoping nobody would bring up that. But,
I'm so sorry.
no, that's fine. I think, and I had this thought when we were focused on the time. It really depends on your assumptions, right? So I'm making some pretty. I mean, this assumption of the time of 1,000 is a pretty extreme value. So I wouldn't focus too much on the actual values. Those are very large. So they are very large. It depends on your assumptions, and we could debate about your particular problem and so forth. So hopefully it goes down with better things. So I don't want to get into many details of that because it really depends on your assumptions. And so
Understandable. Yeah.
Sorry, not to.
What size Heisenberg model is this? Just curiosity.
It's a n by n. It's 2D, and the size is given by this guy here.
Is this Hamming wave phasing, or is this all normal rotation synthesis?
We're doing cubitization, so I don't think they're doing.
This is poly-LCU with alias sampling to do the prepares, and so it's essentially a 2D lattice with XXYYZZ connection couplings in between adjacent nodes on the lattice.
And it's not, but then it's not reaction limited compiled.
We should talk about that later. I'm not sure exactly. I know exactly what you're talking about there. Yeah.
A very high-level question as someone who's not so familiar with this. If you go back a slide, like, are these types of architectures actually like equally viable in, like from a hardware perspective, or are these more idealized kind of pictures that you want to just get a better understanding of, perhaps? Like,
I think they're viable. It depends on who you talk to, right? I mean, I think somewhere in here. This is kind of what I think about for like the bicycle architecture, the Tour de Gros paper. You'll hear about that this afternoon, I think, right? I think they have just 1 factory currently, but yeah, I think people talking about grids, I think they're all pretty viable. I think these are all fairly simple. We can think of much more complicated architectures than this, yeah, which we can support eventually. But
I see. So in the next slide, when you do like benchmark these, you're kind of putting them on equal footing of like, oh, these are all equally viable, and we're just gonna.
Yeah. I'm just calculating the time and the number of qubits required for each one, right? So you can see, like, if you have if you have these private factories, right? You have every block has its own factory. There could be an advantage in the hardware for that because maybe you don't have a really good bus that you don't have a bus that allows you to sort of share factories across everything, right? So that might be valuable, but that costs you a lot of qubits, right? But here, these circuits, we really need to parallelize these circuits better because they're really, yeah. But I think these are fairly simple architectures. I think we can certainly do much more complicated things, and that's what we planned on doing. Yeah. Okay, to go to Max's, what I just promised Max was, so the question is like, how do you map qubits onto these different blocks? And we would also think about this for superconducting qubits too, because the blocks are, I think of the blocks as being locality, right? So if you've got 16 qubits in a block, the fact that you're only operating within a block means you're doing things locally, right? So it gives us some sense of that. Even though superconducting qubits, you could probably do things across the whole machine. And it's a little bit more limited on these QLWC architectures and so forth. So I thought about doing it in 3 ways. One is sort of randomizing the qubit allocations. And you probably wouldn't randomize them. You would probably just put them down in some order, but without thinking about it too hard. But this is a representation of that. Balancing them, so the idea is that you want to sort of balance the operations across as many blocks as you can. And the other was to try to put blocks together based solely on how frequently you do 2-qubit operations. So here again, this is all just 2-qubit operations. There's nothing to, all single qubit operations would always be within the blocks, interblock operation. And so looking at 3 different things, like how often do you do a 2-qubit gate in the block? How often you do it across blocks, and how often do you have to like transit other blocks in order to do your 2-qubit operation? If you look at the randomized thing, you're doing lots of operations, transmodule operations. You're doing a fair number of interblock operations, and you can barely see the intermodule ones, and that's really because you haven't done anything to consider that. But you can do pretty good if you try to balance things out. You have a lot of intermodule operations, a few intermodule operations, and you see the sawtooth because this is a linear thing, and so if you need to talk to the guy at the end, you have to go through everybody in the middle, and that's why you see this. If you localize things, it turns out that this is like a 16 module block, so most of the stuff can be done in one block. So that's kind of cool because that means that there's a lot of operations, there's only a few qubits that use a lot, and there's a lot of qubits that don't use very much. And so that really would be good for architectures that have maybe cold storage and things like this. Yeah. If you have a grid, things get a little bit better, as you expect. This is the linear one from the previous paper, from the previous slide. This is a grid, and you see transmodule things will go way down, and that's great. That's what you expect. And then my second to last slide, in fact, real slide, is to talk about maybe one of the questions that came up during from the organizers was like, what are some of the challenges in this area? I really feel like we're in a time now where we have a lot of different architectures to think about. We have, this is the Google architecture. This is from Athena's paper about the active volume architecture. We have this new Pinnacle architecture. So there's a lots of new I call this sort of, the homogeneous technology, meaning we're all sort of using the same sort of underlying qubits here, but the design now is much more structured, is at different units. Here in the past, we always just had like the same thing, a grid of qubits and things like this. So I think this is really exciting. And then another thing to advertise is DARPA is starting this new program where they're talking about doing heterogeneous technology. So the idea of bridging ion traps and superconducting qubit things and so forth. And so this is something to look forward to starting probably in April or so of this year. Okay, and so I will just stop and say, resource estimation has many steps, starting from the application all the way down to counting the resources. And we think that circuit level analysis is very important. This pyLIQTR is an open source tool where we have a new release coming soon. And I'll just thank all the folks that work on this in our team. And thank you very much.